Hi, everyone. Welcome to Quantum Conversations 15. Today, we'll be hosting Classiq from Tel Aviv, Israel. Their platform allows users to easily synthesize circuits from a set of constraints, which I think they will be speaking about today. And we'll be hosting Yuval and Nir. So Yuval is the Chief Marketing Officer for Classiq. He comes from a STEM background. He did physics for his education, also did an MBA. And he's also known as the Qubit guy. If you are familiar with his podcasts, you can follow him on Spotify. And we have Nir, who is the co-founder and CEO of Classiq. He did a master's in electrical engineering. He also had executive roles at the Israel Defense Forces. So as you are well aware, if you have joined to our previous sessions, I ask everyone to introduce themselves. And you don't have to do this, by the way. I'll just give everyone an opportunity to say hello to Yuval and Nir and give their name, tell us where they're visiting from. This could be a place or an institution, and why they're interested in Classiq or quantum computing, quantum information sciences, or deep tech, why they're here today. And I'll wait for I'll call everyone's name and I'll wait for 3 seconds. So if you don't want to speak, that's fine, and then we'll pass. Otherwise, you can have a chance to say hello. Maybe let me go first. Hi, I'm Mert. I'm visiting from University of Oxford, and I'm interested in Classiq because it seems like a great tool to be to generate circuits automatically, which could take a lot of time if you're just doing it by raw code. And maybe our speakers can do this small, brief intro, and then we can go around. So Yuval, do you want to go now?
Yes. Hi, I'm Yuval. As Mert said, also a Qubit guy. I live in the Midwest, and happy to be here.
Great, thanks. Anuj Mehrotra.
Yeah. Hi, this is Anuj from India. I'm part of a emerging technology startup based in India. Thank you.
Bamborde Balde. Okay. Bob Miller.
Hi, I'm Bob Miller. I'm just interested, my background's in mathematics, and I'm just basically interested in quantum computing in general. I'm from Haddonfield, New Jersey.
Nice to meet you, Bob. Damien Weldon.
Hi, everybody. I'm Damien Weldon at the Molybdenum in the San Francisco Bay Area. My focus is in quantum computing applications in financial services and finance. Great to be with you all today. Thank you.
Great. Finance. Okay. Dan Litowitz. Okay. David McMahon, who's I think a student here with me at Atomic Laser Physics at Oxford.
Hello, Marsh. It is me. I'm David McMahon. I'm studying atomic and laser physics at Oxford. I am very interested in quantum computing, based from the computing perspective and also the possible applications in quantum chemistry. What I'm studying right now, laser wave field acceleration, that has significant potential to improve chemical imaging and other nanoscale techniques. And so I'm also very interested in quantum computers and how that can be applied to help understand the complexity of nature, which tends to be shown through chemistry. So thanks for running this talk, Mart.
Yeah, thanks, David. Emil Dimitrov.
Yeah. I'm a computational scientist with the Irish Centre for High-End Computing here in Ireland. I'm involved in a number of quantum computational projects, and always good to hear from the Classiq guys. We are chatting them as well directly.
Cool. Deb Ghoshal. Okay, Dimitri.
Hello, I'm an applied mathematician and software scientist based in San Francisco. I have a lifelong love of physics, and my interest in quantum computing is at the moment is just researching as a hobbyist, but this may change. That's it for me.
Thanks. Jamie is one of our regulars.
Hey everybody, hey Mert, thanks. Yeah, I think we're at Quantum Conversations number 15. So I just wanted to kind of link it together a little bit and say that number 14 was I'm at Wisconsin-Madison studying quantum computing. So one of my professors spoke at the last Quantum Conversations, and last semester, Yuval was our guest speaker in class when we wanted to talk about industry and applications in industry. So that's how I met Yuval, and yeah, that's cool to hear him talk again today.
Cool. John Willis.
Hello. Yes, I'm from the Washington, D.C. area. My career is actually in cybersecurity. My interest is I've been following the work there with Bob Kuka and the QNLP stuff there in Oxford. I'm quite interested in that from a cybersecurity log monitoring perspective, but also keenly interested in some of the applications to chemistry and the quantum computing, quantum chemistry area. Thanks.
Right, thanks, John. Also, for people who are joining right now, I'm just calling up names. If people want to introduce themselves, you don't have to say anything if you don't want to speak up. And also, if I miss you, please at the end just shout out and do your little intro. Kunil Kawandla.
Yeah, it's actually Sunil, but yeah, that's okay. I'm interested in quantum computing just for interest's sake. I spent the better part of the last 2 years working with transpilers, doing custom query languages, and now that's got me kind of curious as to is there a way of working with a transpiler to actually create the programs that, you know, like QuConv for quantum computing. So, you know, I haven't really picked a front end yet, but it'd be nice to just do it using natural languages.
Cool. Maha.
Oh, and I'm from Dallas, by the way.
Maha.
Hello, everyone again. My name is Maya, also Maha. It doesn't matter. Pronunciation is the same. And I'm still an ML engineer and still wanting to learn quantum computing and especially quantum machine learning. And I'm here in Europe and happy to connect to all of you. I see very familiar faces once again, and I'm happy to be here.
Yeah, nice to see you again. Thanks. Nathan actually helped me organize this event. So thank you so much, Nathan, for going through the struggle of like getting people together.
Hi, I'm Nathan Shore. I'm in San Francisco, and I'm a 74-year-old student. I've always had a fascination with math and physics all my life, but wasn't disciplined enough in my dissolute youth. So when I retired 4 years ago, I decided to start studying math and physics, and there was quantum computing coming out. So it was a nice fit. So because I have an IT marketing background, I put some of those skills to use by helping people organize events and getting more people to show up like I did here. And by the way, I'm planning one at UT Austin on April 11th with some 3 powerhouse speakers, including Scott Aronson, who I'm sure everyone's familiar with. I'll put the link in the chat in a minute. And I also have, to get people interested, I put together a site called quantumcurious.org, which is content curated only for beginners. When you first get into this field, it's a fire hose. How do you figure out, you know, what to study? Most of it is highly technical. So I just curated information that was dedicated to beginners and put it on that site, quantumcurious.org, which I'll put in the chat too. So it's really great. We have these kind of, you know, informal meetings periodically, so we can all get together. You know, people here have PhDs and are deeply into the field, and there's people on my end who are just beginning. So we need more of these kind of events. And I'm glad to see, wow, we got 25 people actually here. That's wonderful. Thanks.
Yeah, thank you, Nathan. Kwanzi Bakari.
Hello, all. My name is Kwanzi Bakari. My background is actually in astrophysics and particle physics from UCLA. I'm interested in quantum information science and quantum computing, and thank you all for having me.
Nice to meet you. Sami Kamkar. Hi, sorry, we're just eating something, I think. I think you're still on mute. Wait, you can't hear you.
Sorry.
Yeah.
How about now?
Yes, this is good.
Oh, awesome. Sorry about that. Hi, I'm Sami Kamkar. I'm a reverse engineer in Los Angeles. And I've been working on designing and fabricating an optical quantum computer, because a lot of the stuff you can actually do DIY. So working on that and really interested in QASM and similar systems. So this is really interesting to me. Thanks for having me.
Amazing. Sasha K. Sasha. Okay.
Oh, wait. Hi. Sorry. Yeah, I'm Sasha. I'm from Buenos Aires. I've joined a few of the quantum conversations already. Yeah, I'm a quantitative developer, so trying to learn how to use quantum things to do some optimizations and all the stuff. Yeah.
Okay, nice to meet you. Shreya Satsangi.
Hello everyone, so I'm from India and I'm currently an undergraduate student from physics and cognitive science. Thank you, nice to meet you all.
Nice to meet you. Shweta. Okay. Stephen Labag. All right. And Veso, really nice to see you again.
Nice to see you again. I'm really glad to see that there's a lot of people that are coming here regularly. My full name is Selin Georgiev. I'm mentor for the Quantum Open Source Foundation and work with students in QWorld research. I'm currently teaching a new course for Quanterao, which is a software company in Europe. So I shared my link in file and information. So I'm interested in quantum computing since my background is physics, quantum physics, and naturally kind of connects. And that's why I'm doing all these efforts and work related to my two institutions in United States and Europe. So if you want more information or connect with me, feel free to connect with through LinkedIn. Thank you.
Thanks, Veso. Berat.
Hello there. I'm a master's student at RWTH, and right now I'm currently in Turkey, trying to learn what we can do with these things.
Amazing. Okay, cool. Yeah, if I missed anyone, please shout out. Otherwise, we're gonna go ahead and get started.
I think Nir joined us, so.
Yeah, I mean, yeah, and Nir, we were doing quick intros. I already introduced you, but if you want to say a quick hello before Yuval goes on with the presentation.
Hey, it's a great pleasure meeting you all, and I'm very much looking forward to the discussion.
Perfect. All right. Yeah.
Quick question. There's a lot of interesting content in the chats. I know there's a way to download the chat in one shot. The text. Does anyone remember how to do that on Meetup? There's a lot of good links in there.
Yeah, I mean,
yeah, if you go into chat and if you click on the three dots, you can click save chat, and that will
thanks a lot.
save for after the meeting.
Thanks a lot. Sorry for the interruption.
Yeah, no worries. Yeah, thanks, David. All right. Then I'm gonna make you the host too. Also, I think you can still share your screen, but thanks for everyone.
Not yet, but soon enough.
You can't right now?
No.
Okay, let me make you the host then. Here you go.
All right, thank you very much. So I think that it may be a good idea to set the stage with a short presentation, and then we can do a demo, or we can do a Q&A, or we can talk about whatever you guys want. So we're here for you. So we think that at Classiq, we have the best way to design and deploy quantum software algorithms. So let's talk about why this is an issue, when will it become an issue, and what we can do about it. So just briefly about Classiq, company started in 2019, headquartered in the US and in Israel. We have, I think by now, close to 40 quantum software engineers and scientists, raised about $50 million from inception. We're Series B closed a few weeks ago, and we were featured in Times Square, as you can see on the right side. And we have both interesting customers and partners, from AWS to NVIDIA to NTT and others. So there's a lot of stuff going on. As we know, quantum is getting closer to the mainstream. This is a survey that was done in December of last year, and it shows that about 30% of companies are in early or advanced adoption stages of quantum. And you see a lot of the logos on the right coming from various fields, from financial services, from defense, from transportation, chemicals, pharmaceuticals. They all have quantum teams. They all have varied interests. So something is happening. And of course, to be quantum ready, to be able to extract the business value from quantum, you need a combination of hardware, which hardware itself usually hosted on the cloud, and software. If you just have hardware, it's going to be useless. If you just have software, it's going to be useless. But working together, you can get the business value that you're looking for. The issue is that as we go from toy circuits and toy problems to real circuits that solve real problems, the number of qubit increases, and the methods that we used to design circuits when we had 5 qubits or 10 qubits are no longer possible to use going forward. This is not new to quantum. I mean, this is new to quantum, but we have seen it in other fields. Today, not a lot of people program in assembly language. Not a lot of people create web pages using raw HTML. I mean, we use Python and C and Wix or Webflow or WordPress for these purposes. We don't do statistics on a calculator. We do that with R. And so that progression of going from something that's very, very low level, very close to the hardware, to more abstract functional model is something that we've seen in all fields, and we believe that we're going to see it now in quantum. So when you look at implementing quantum algorithms, it's not rocket science, but it can certainly sometimes feel like it. When you look at articles such as this one, this is an article from Goldman Sachs and University of Maryland and IBM on how to do derivative pricing in quantum. So it's a very long article, and as you can see on the right side, it has a couple of appendices, and one of them shows the recipe for what they're trying to do. So here's the payoff implementation, and they go step by step, right? So if you look at step number 7, we control copy all registers controlling this and in these conditions. And so a lot of companies say, okay, I saw this article, I would like to do derivative pricing, or I would like to do chemical simulations, or I would like to do quantum machine learning. How do I implement that? How do I get that? I want to implement that on some platform, see that it runs, and then take it from there. So make progress, make changes, implement my own algorithms, and so on. And so the process today is that you take that desired functionality, you take pre-existing blocks that someone created for you, or maybe that you created, maybe a state preparation block, maybe a block that does some arithmetic, and you try to combine them together and try to optimize them. And at the end, you turn it over to the automatic sort of compiler or transpiler to take the last step to make it ready for the hardware. The problem with this process is that it's super complex, because at every one of these steps, you as a designer have to make a lot of decisions. On the individual blocks, every block could have multiple implementations. So for instance, if you just need to add 2 quantum registers, you could use a QFT adder, quantum Fourier transform adder, or you could use a ripple adder. If you knew that you have more qubits, you could make a circuit that's shallower, that's shorter. If you don't have that many qubits, you might need to make it longer. What is the level of accuracy that you want in each of these circuits? But then when you try to combine all these blocks together, you run into system-wide constraints. How many qubits do I have in the hardware that I want to run on? What is the noise characteristics? How deep can I make it? Should I reuse qubits or not reuse qubits? What is the specific hardware? What is the gate set? And even if I can do all these things, 3 months later, there's a better computer or a larger computer, and I need to redo them again and again every time I want to move to bigger and better hardware. So that's sort of a big pain. And by the way, I forgot to say that if anyone has any questions, feel free to just shout out or do them in the chat. Happy to answer them at any time. And these issues, the block level decisions and the system-wide constraints are interconnected, because if you see, oh, I've ran out of qubits, then maybe you want to go back to the block level and say, oh, I'll use fewer ancilla qubits. And so this is sort of a big and very difficult process. Well, what customers want to do, what enterprise customers that we speak with want to do, is they want to learn how to do this themselves. They don't want to continuously rely on consultants. They understand, they believe that quantum is strategic technology, and they want to be able to build circuits themselves. They want to build circuits that scale. So a financial services firm might say, yeah, I know that with today's computer, I can balance 5 assets in my portfolio, but that's not interesting enough. I want to be able to balance 500 assets tomorrow. I want to determine which hardware is best for my given problem. I want to be able to take experts in financial services or logistics or chemistry and integrate them into the quantum team. I can't just rely on quantum PhDs. There are not enough of them. I want to be able to prototype quickly so I could figure out which problem is best suited for a near-term solution, and so on and so on.
So you are, sorry to jump in. So you were saying about like any hardware, but you're meaning gate-based here, right? Because in terms of...
Yes, we focus on, you're correct. We focus on gate-based hardware. Yeah. And as you know, even D-Wave is now saying, well, we understand that annealing is useful, but has limited usability. So we're also starting, D-Wave are also starting to develop gate-based hardware.
Are there any, just like a question on that, are there any other kinds of design or kinds of architecture that you were considering for that? Or why is it that it's a more gate-based as a design for the architecture?
So when you look at the collection of manufacturers, most of them are doing gate-based hardware. They could be using different technologies. One could be using superconducting, and the other could be using trapped ions and maybe photonics and maybe this, that, but sort of the prevailing architecture, the common architecture is a gate-based architecture. Now, every vendor might have different number of qubits or different connectivity or different noise characteristics and coherence characteristics or different native gate set, but we want to allow the broadest possible range of solutions on the broadest possible hardware, and that's why we focus on gate-based design.
Okay.
So what we do is and this is a big statement, so we'll decompose it in a little bit. We convert high-level functional models into optimized gate-level code. So instead of asking you to work at the gate level, connecting individual gates to qubits and so on, we ask you to define what is it that you want the circuit to do and what your constraints are, and then we automatically convert it into optimized gate-level code. So while the approach is new in quantum, it's not new in the world. This is when Nir and the other co-founders started Classiq, they were inspired by the process of classical design, electronic design. So what you see on the right is an electronic circuit. It's not a quantum circuit. It has and or not gates. And at least for me, it was difficult to tell from a distance what it does, and it would be even more difficult to change it or to debug it or to scale it up. And this is a simple circuit. This has, 100 gates, but we are all using Zoom right now on computers that have billions of gates. Well, how were they designed? Well, they were designed using high-level functional models. So the circuit on the right was designed with the high-level model VHDL on the left. And so you see here, now this is much more human readable. You can see that it has, you know, an adder, and it looks like it's a 16-bit adder, and it looks, and you can define the behavior. And then you have software programs like Cadence or Synopsys that take that high-level model and synthesize it into an electronic circuit. Well, we do the same for quantum. So we allow you to
code? Sorry, well, is this a one-way mapping where the code, both in the Classiq case, also now you're showing your code, which is the quantum case. Is that like each series of lines, when you have a whole code structure, does that lead to one mapping, or is it one-to-one, or you can have multiple circuits?
Well, you could have numerous different circuits that implement the same functionality. So just to go back to an example I mentioned earlier, you can say I'm going to do a QFT adder, or I'm going to do a ripple adder. I have more qubits or fewer qubits. If some of the terms in a Hamiltonian, for instance, are commutative, so you can decide which one you're going to do first. For instance, let's just take a mathematical example. Let's say we want to we have two quantum registers. One is A and the other is B, and we want to calculate A squared minus B squared. Well, we could take A and square it, and take B and square it, and then subtract one from the other. But we could also calculate what A plus B is, and then multiply it by A minus B. So here are two equivalent or mathematically equivalent ways to do the same thing. And the right answer depends on your constraints. What are you trying to say? What are you trying to achieve? What's important to you? So we allow you to define a high-level functional model of the circuit. You see here a Grover operator. I'll show this live in a little bit. And then we basically synthesize it. We convert it into a hardware-aware quantum circuit that you can immediately execute on the cloud provider of your choice. So the workflow is basically as follows. Our side is sort of the yellow blocks on the left. Our input is both a high-level model, you know, what is it, the functionality of the circuit that you're trying to deliver, as well as the constraints. How many qubits, what's the gate set, what's the width, what's the accuracy, and so on and so on. And then we synthesize it. And our output is Q sharp or Qiskit or Chasm or IonQ or Bracket and so on. And then we go through the transpiler or compiler and then go to Azure or AWS or IBM or IonQ or others, basically any universal gate-based computer. So we allow the designer to focus on what they want to do, and we explore millions and millions of options in a very big design space and find out the how, find out the optimal how. So if we think about the process that I showed earlier, we automate most of it. So your job as a designer is now basically just to define the desired functionality. And then we've packaged dozens and dozens of man-years of expertise in the box, essentially. You know, we have a lot of algorithms. We know how to organize them. We know how to optimize them. We understand the hardware. We understand all the things that can be done to deliver an optimal circuit or an optimized circuit for the hardware of your choice. And as a result, by focusing on the what, not the how, we can build, and I'll show you in a second, we can build quantum circuits very quickly and very large ones. We can dramatically reduce the quantum resources, because today computers are limited in the gates and the qubits and the depth and so on. So for instance, we did a test where we took, for chemistry application, we wanted to create a circuit that calculates the ground state of water, H2O molecule. So we used a state-of-the-art tool from another vendor, and that generated a circuit that was about 6,000 gates. And then the same problem, which yielded the same numerical results with Classiq, was only 3,000 gates. We were able to do the same problem with half the gates because we have a bigger design space that we can optimize on. We can dramatically reduce the development time, and as you'll see, a lot of the code that we ask the user to write is not quantum code. So they could be a chemistry expert or a QML expert or a financial services expert and still generate highly optimized, very useful quantum circuits.
Can I ask a question?
Please.
Regarding the mapping, the compiling part, I was curious about like when you actually use an initialized state code in any one of the providers like Qiskit, it actually gives you an overall circuit. But when you actually want to run it on the quantum computer, it has to be dissolved in the basis gate sets of the relevant quantum computer. And this procedure, from my experience, can increase the gates and like the number of gates you have in the circuit quite a bit. Do you perform any work regarding this in your application?
Well, yes. I mean, in a couple of ways. One, we allow you to very quickly move from one computer to another, and as a result, from one transpiler to another. So you might have a circuit and you say, well, let's see, can I fit this on a Honeywell computer? Can I fit this on an IonQ computer? Can I fit this on someone else's computer? And you could very quickly move from one to the other. The other thing that the one reason that the transpiler that you mentioned could increase the number of gates is that the gates that you have in the code may not be the fundamental gates, the basic gates that that particular computer is using. So it has to basically say, oh, I don't have a control Z gate, so I'm going to implement them using this and that. We allow you to define the native gates, and therefore we believe that our output is going to be much, much closer to something that's going to be very efficient. I also want to just highlight the difference between what a transpiler can do and what we can do. So a transpiler can, for instance, look at two consecutive Hadamard gates and say 2 Hadamard gates in a row is an identity gate. I don't need to have 2 Hadamards, I can just cancel them out. But what we can do is, for instance, say, let's assume that you as a designer said, I have a QFT, a quantum Fourier transform block, and then a QFT dagger block. We understand that these cancel them out. So we understand your intent. We can go back and say, what if we had more qubits? Could we have it more efficient? We understand that you're trying to do quantum math. The transpiler doesn't understand that. The transpiler just sees a list of gates and their connectivity. And because we understand more about your intent, we can have optimizations that are much superior in that regard.
Thank you very much.
Meredith, I think there were maybe 1 or 2 questions on the chat. Maybe you can help me there because I don't want to open the chat and lock the presentation.
Sure. Yeah, I think it was just comments. I don't think there were
comments. Okay. So
I have a question if you have a minute. Maybe you're going to address this later, but it's a very comprehensive product you're presenting. So if someone was interested, a customer, for example, to engage with you, could you talk, maybe you're going to do this later. How would that work? Do they hire you as a consultant? Do they get a package? Is it something on the cloud they get access to? Is it a download? How does one interact with this facility?
So what customers typically do is they have a business problem they need to solve. So maybe the customer was tasked, CIO came to the quantum group and said, you know, I'm really interested in quantum finance. I want to do option pricing calculation using quantum and see if that could be a fit for our organization and compare it with what we get on classical computing. So they often know what problem they want to solve. They come to us and they say, we want to do option pricing. And maybe we want to do it using these and these articles that we saw on the web. Our goal is not to write the software for them. Our goal is to teach them how to use our platform so they can be self-sufficient. If I were to simplify it, we're not giving them a fish, we're teaching them how to fish. So we would work with customers for a couple of months and guide them on how to create that algorithm using our platform, helping them along the way. And then when they're ready, we sort of take off the training wheels and say, now you're on your own. You can always call us for support, but you can build your own IP, you can make your own progress. You don't need us, you just use our software license to continue and do your work.
So in effect, it's like in the classical world, you're selling them a software license and accompanying that with consulting services so they can optimize the product to their problem. Is that fair?
Yeah, I wouldn't even call it consulting. I would call it training. Basically say,
you're right.
We'll teach you how to use the product may not need customization. We use training.
Sure. And they might already have some expertise, or they might have none. Okay, that was very clarifying. Thanks.
Very good.
We have a question on the chat as well from Bombarde. In terms of quantum hardware technologies, which one do you see your customers using the most? Also, what use cases are they leveraging more your abstractions?
Sure. So in terms of hardware, I mean, most quantum computers are hosted on the cloud these days. So we have customers that use AWS, and we have customers that use Azure, and we have customers that use IBM, and we have customers that want to directly connect to an IonQ computer or someone else. We've certainly seen a gamut of applications. Quantum is a horizontal technology, right? So we have customers that do financial services. In financial services, we have a customer in the defense field that does something very cool to track objects in the sky. We have customers that are looking at chemistry. We've got customers that are looking at logistics and so on. Now, a lot of the functionality of our platform is horizontal. It's applicable to multiple fields. But then we've also built application suite. So if you do want to calculate option pricing, here's an example how to do that. If you do want to calculate the ground state of a molecule, here's how you do that. If you want to do traveling salesperson or max cut or a 3-sat problem, we'll show you how to do it with our optimization toolbox. You can almost think about it like MATLAB that has a very strong underlying engine and then packages on top of it that are tailored for specific use cases. And so, for instance, here is what the code on the left side looks for someone who wanted to calculate European call options, option pricing. And if you look at the code, other than the first two statements that say I've got 20 qubits and I want a certain circuit depth, everything else is essentially about finance. It's not about quantum. It says, well, I've got log normal distribution, and this is the threshold, and these are the parameters of my distribution. And then the circuit on the right is what's generated from our platform. And of course, each of these blocks has many, many gates and components inside it. And I'll show you how to dive into that. Here is an optimization problem. We deliver the code either as a plugin to VS Code, Visual Studio Code, or as a Python library. So here's someone that says, okay, I have an optimization problem. You see it on the left, and this is the circuit that was generated on the right. So maybe this is a good time to just run a few circuits for you. Is that appropriate?
Yeah, that'd be great. We also had a follow-up question in the meantime.
Please.
Yeah. So are your customers using mostly superconducting hardware? By Bombardier asked the previous question.
If they're using primarily superconducting hardware, I'm not sure. I don't know if Nir is available, but yeah, do you know?
Yeah, most of the users today try to be as diverse as possible. They want to try various modalities, usually iron traps, superconducting qubits, cold atoms to some extent, and and simulators, which today are probably the best way to go. So no significant emphasis on superconducting qubits.
Yeah, I just read about your recent partnership with NVIDIA for simulations. If I'm correct.
Yes, and that's an exciting partnership, and what it allows to do is to get people ready for larger scale computers. So basically saying you can use the simulators because they could be noise free, and you could see how the algorithms would behave with large number of qubits, and then you'll be ready once the hardware is there. Can you see my screen, by the way?
Yes.
Okay, very good. And is the font large enough?
Yes.
Perfect. So I'll show you some of the VS Code, the Visual Studio Code example. Start with a very simple example. State preparation is the process of initializing qubits to a certain value. That's sort of fundamental to very many algorithms. Here we have a list of probabilities that we want to load, and actually also the accuracy, how accurate we need them to be. We specify that we want 4 qubits, and we specify the output as QASM in this case. And all I need to do is to write generate quantum circuit. And now this is live. So this was just sent to the cloud. And now here is a quantum circuit that delivers this functionality. And on the right side is the QASM code that does it. And by the way, if I don't want to do QASM and I wanted to do Q#, for instance, then I just change that to Q# and generate the circuit again. And here's Q# code, same thing. Now, I might say, okay, well, this is good, but what would happen if I wanted to make the circuit even more accurate? So instead of 5% accurate, I'll make it 1% accurate, generate another circuit. Excuse me. And now you can see that the circuit has become larger, is longer, because we need to work harder to get to that higher accuracy. So this was a simple one. Let's do something fun. One of the things that you often want to do is a Grover search. And in a Grover search, you have to have an oracle. Sort of the function says, did I find a solution or not? So here we have a really simple example. We have 2 quantum registers, A, which is 3 qubits wide, so it could be up to 7, and B, which is 2 qubits wide. And here's the expression we want to fulfill. A plus 5 XOR B modulo 8 equals 2. That's all I need to do. And now if I want to generate this, let's call it MERT, just for a reason that you'll see in a second. And voila, here is the circuit that delivers this. So this is the Grover search. You can see here the adder, the XOR, the equal, the cleanup, and then the diffuser. And if I wanted to just take even a deeper look, let me open the file panel here. And I think we called it MERT, right? So let's find MERT along the gazillion demos that I have here. And here's MERT with today's date. And now I'm going to look. So I have the QASM code, the transpiral QASM code. And now I'm going to open and try to see the circuit itself that was generated. Let me just move it to the screen so you can see it as well. And I'm going to share that window instead because I opened it in a browser. Very good. So here you have the circuit that we just generated. And now I can interactively go deeper and say, this looks exactly like what I showed you before. The adder, the bit XOR, the equal, the dagger. Now I can go into the adder and say, oh, okay, so I have a QFT adder. And now let's see how QFT is implemented. So I could go deeper and deeper and deeper and really explore and figure out what the Classiq software did. Underneath this, what you may be realizing is that we just, within a few seconds, essentially, created quite a sophisticated circuit, and which, at least for me personally, would take a lot of time to create manually if I could ever do it. And here we just created it in a matter of seconds. I know there are some finance people. So here's what a finance demo looks like, right? Same thing, here, number of qubits and all the other things that are going on. Let's see if that executes. And I could get a circuit that does this function, and so on and so on. So basically, just to wrap up and leave time for questions, we have a new way of designing quantum circuits. This new way takes high-level functional models and automatically converts them into optimized hardware-aware circuits. So you can focus on what is it that you're trying to do, and let our experts, sort of packaged in the box, figure out the best way on how to deliver that. So with that, very happy to take questions. Nir and I are very happy to take questions if there are any.
All right, cool. Really great demo, really exciting product. Thanks you all. Let's go with the stuff that came up at the chat, and then we can also shout out the questions. How do you handle error mitigation? That's a question from
yeah, definitely. One of the beautiful things about designing circuits at this, at a functional level, is that you can define the functionality you want to achieve, but then embed other constraints. And a specific hardware noise model or error mitigation schemes could be embedded in the high-level model, and then you get a circuit that is synthesized, with the error codes and and so on embedded.
Okay. Could this approach also generate OpenQASM 3.0 code?
Yes, it does OpenQASM 2.0. It does QIR, QSharp, Circ, and sometimes we can even work with vendors to create the format that they want to work with.
Sorry, it was OpenQASM 3.0, not 2.0, 3.0.
Honestly, I don't recall, but if not now, so in a few weeks for sure.
Question from Berat regarding the max depth parameter. Does these enclosed box count as one operation? Berat, would you like to maybe clarify the question a bit?
Yes, when you first printed out the circuits, there were like the picture version in which there was this enclosed one, then you opened up the demo, then you could go in further. Does these enclosed versions, which are just like fixed operations, are they counted as just like one operation depth, or does the algorithm also counts how many gates they enclose inside?
The depth is counting fully expanded circuit.
Okay.
It would have been fun to count only one, but we can't afford that.
And I had another question, but let me just read it. And when a user interacts with your software, can the user provide a specific connectivity of qubits so that your God damn, it's a really nice product.
Exactly. This is a great question. Connectivity is one of the hardware constraints that obviously if you need to tailor-made the quantum circuit for different machines, so different connectivities would make it very, very different, and you can embed it in the high-level model, and then the synthesis engine is doing the hard work. So yes, the answer is yes.
Okay. And we also have a follow-up for error mitigation. Which error mitigation protocol do you use?
We use several of them, to be honest, and nor me or Yuval are the error mitigation experts. Usually what we do is embedding the error mitigation codes that our customers embedding in their models, right? We don't have any restrictions. We are not bounded to specific one. It's really up to the user. So it's not a good enough answer, but this is the right answer. And I'd love to elaborate in offline on deeper dive into it.
I have a quick question about Classiq's position in the quantum computing commercial landscape. It's like I mentioned before, it's a comprehensive product. It seems like you guys invented or developed or this technique. I mean, it seems like a no-brainer. Why would somebody not use a product like this? It seemed very inefficient for them to do it on their own without your help. So Classiq sort of, is that true? You sort of invented that help connection between the hardware and the software? Or are there other people out there doing similar things?
I think that one of the beautiful things about this ecosystem right now is it's evolving very fast, but evolving. And there is a great advantage to fast movers. So we were the first one to establish this layer of the stack, the layer of high-level modeling and synthesis of quantum circuits on top of gate-level programming languages, which, from them you have definitely several of them, Q# and Qiskit and Cirq and many more. So we are the
That's
first.
what I meant about comprehensive.
Yes. Thank you for saying that, Nathan. So we do believe that currently it's a very unique product, and we hope that more companies will go to the same direction. Competition is good for the ecosystem.
But is there anyone that is distinctly offering something like what you're doing? It seems like you have a unique approach.
Currently, it's unique.
Pardon?
Currently, it is unique, definitely.
Great. Thank you.
There's a question on the chat about debugging and testing of the circuit. And yes, so first we have some pretty extensive capabilities. One of them is to analyze the circuit, to tell you what the entanglement level and what the connectivity will look like on particular hardware, and which qubits are busier than others, and sort of I'll create heat map and so on. So to help you figure out the optimal implementation. That is also one of the reasons that we've partnered with NVIDIA, so we can have higher end simulators that do allow you to break and figure out what the value is and so on, things that you perhaps couldn't do on real quantum computers. But the question of scaling is not just about how do you create a circuit for 500 qubits, but it's also how do you debug a circuit for 500 qubits, because you can no longer simulate it on a classical machine in most cases. And that's certainly an area that we have some capabilities and we continue to think and work on.
Okay, there's another question on the chat from Suna about the backend, about the structure of the optimization and all the synthesis procedure.
Are we using Antir? And I'm not familiar with Antir.
Okay.
No, we are not. We are using a combination of our own synthesis engine developed in Classiq and other methods like mini-zinc engine, and now having some commercial synthesis engine by some of the more familiar players from the classical field.
So if we go over the product, we have the higher level, the platform, let's say, we have the higher level code that goes to your cloud, right? So that it's not done on the spot on our devices. It goes through the cloud, and it's done, I guess, through like some high performance computing structure, maybe GPUs on your end, and then comes back to the user. Am I correct?
You don't need an HPC. Even the synthesis of thousands of qubits is something that is done in few seconds, sometimes few minutes on the cloud, on the AWS cloud. It could be done, by the way, also locally. It's not, we are not doing anything that is exponential in nature, because otherwise it wouldn't scale, right? If it takes a few hours to do that for a few dozen qubits, so it would probably take too long to do that for 20,000 qubits. So we make sure that everything is scalable. But yes, the backend is usually on the cloud. You generate you model the circuit on your machine, you send it to AWS, and you get the quantum circuit back. So and then you send it back to running it.
So why is the choice to do it on a cloud structure then, if it's easily done on a device that's local?
A SaaS model is something that our customers like, because then they don't have to worry about the compute infrastructure to synthesize the circuit. They don't have to worry about software upgrades, and so on and so on. For those customers that, for whatever reason, do not want to send their circuits momentarily through a secure connection to the cloud, then we can also install the synthesis engine locally.
Cool, I see. Okay. And in terms of the optimization part of things, so that goes back to my earlier question on if there's a one-to-one mapping from the code to the circuit. And I understand that from a functionality standpoint, there are many circuits that can have the same function. But first, there's the code that we generate as the user, right? That translates into a circuit. And from my understanding, and I might be wrong, circuit optimization is a very difficult problem. To get the most efficient circuit, I think is NP hard, but I might be wrong. From like a functionality standpoint, to optimize circuits in such a way that in the end you end with the most optimal circuit that can run on that existing hardware. Are you in some way like looking through all possibilities and getting the most optimal circuit, or is it some other neat trick that allows you to do a circuit that's efficient enough?
Yes, so I'll divide the answer into two. First, you don't need to scan all options. You use methods like pruning, which are also used in the classical circuit design synthesis. And another aspect is the user can define optimization criteria and what are the constraints. So, for example, if you allow the synthesis engine to use 20 qubits and potentially it could do it with 6 qubits, so when it reaches 20 qubits, it's good enough. You can configure and you can ask it to do the best, but it's really up to you.
Okay, very cool, very cool. Is that also like the big question? Is that where the name comes from then? Classiq, from Classiq circuit synthesis?
Yeah, it's a classical development of quantum circuits in a way.
Cool, all right. We have another question on the chat, but I think, is someone gonna shout? Berat, are you gonna?
Yes, I was wondering if you are or planning to provide, for example, Qiskit is allowing you to use a pulse feature to allow like tri-level quantum states instead of just two-level quantum states. Does your software provide this, or do you plan on providing such functionalities?
So we do have plans to synthesize circuits directly to the pulse level. It has some benefits. Usually our users, in enterprises and also in academia are more focused in generating, QASM, for example, or QRR, because then they run it on the cloud, on Bracket, on Azure Quantum, and so on. But some users do want to optimize until the pulse level. So this is something that we want to support as well. Yeah.
I think David has a question.
Yes, thanks for the talk. When you were showing the examples in VS Code, I was trying to understand your syntax, and it's quite unfamiliar to me. In classical computing languages, Java, Python, they all have their own idiosyncrasies and syntaxes. So I was wondering, why did you decide to structure the grammar and syntax of your high-level language as you did? What was your design idea when you were making it?
Sure. So, okay. So first, we have two delivery methods. One of them is what Yuval showed, which is the VS Code extension, which is the textual model, which is the basis of our, diagram block, visual design of quantum circuits, like a Simulink in a way, if you are familiar. So this is one way to model quantum circuits. The other way which maybe we can show is a Pythonic SDK, right? You develop in Python. Obviously, it's our proprietary modeling language. We would love to use another one, but there isn't another quantum modeling language in this level of abstraction. So we needed to invent it, right? So I guess this is the combination of the answers, but you are fully correct that the VS Code, the textual model right now, is not as intuitive as it should be, because it is the basis to the visualization of building these circuits. And the more programming like quantum modeling language is the Pythonic SDK.
And what just to add to what Nir said, if I show you what you see on the screen is a portion of our documentation, and you can see this is an amplitude estimation example. Here is what the code that you would use in VS Code, but for every example, there's also the Python equivalent. So you could work in Python. Some people find it easier to start with VS Code because it's more interactive, but then sometimes move over to Python because then they can use a wider range of classical Python libraries for I/O, for graphing, and so on. But we offer both models to the user.
Okay. Very interesting. Thank you.
Very good. So I don't know, Merit, how we're doing on time, but if anyone wants to talk to us after the meeting, you're welcome to connect certainly with me on LinkedIn and with Nir. You're welcome to email us at hello@classiq.io. And we'd love to talk to you about your requirements and how we can help you create and deploy optimal quantum circuits.
Okay. Well, if there's anything, please shout out your questions. Otherwise, we're gonna conclude the session. I'm gonna stick around for like maybe 5 more minutes if you want to keep on chatting. But I'll stop the recording now if you don't have anything else to ask. Oh, I think Jamie. Oh, Jamie's not a question. He's clapping. All right. Thank you, Yuval and Nir. This was Quantum Conversations 15. We hope to see everyone on our 16th session. We're closing in on our 2nd year now. Right. Thanks, everyone.
Thank you.